is basically about facial recognition. My name's Danny Uzel, and I'm a software developer at a company called ThoughtWorks. And my journey into technology has been a bit different. Oh, sorry. But I guess so. I started out doing physics, and that was largely because I enjoyed music. And then I went on to become a teacher, and then I became a software developer. So, how did I end up in or being interested in facial recognition? Well, when I started as a developer, I ended up going to China. And I remember seeing somebody pay for their coffee with their face. And I basically thought, oh, wait, hold a minute. I mean, the passport gates at Heathrow can barely detect my face half the time. So how on earth is somebody actually paying for things with their face? And so I got into it a bit more and looked into it a bit more and found out a whole load of different areas where people were using your face to define you. And one of the funniest ones I thought was basically this idea of using your face to determine your gender. And I came across an application that was very similar to this one. I mean, why on earth would you want to define someone by their gender via their face? But here we go. So I could say, for example, take a photo like this, upload it, and get a result like this. And, of course, some of the faces aren't recognized, but there's one face in this background that seems to detect them as a male. And that is obviously a picture of females. So I don't know, try a few more, might just be an anomaly. So let's say take a popular one, Oprah. Okay, so we can upload Oprah. She's okay. I mean, she's come out about 0.99 as so 99% chance as a woman. But we know that this kind of technology doesn't really fare well when people have really light or really dark skin. So let's try this person. So they have now been recognized very likely as a female. And let's take one of my favorite actresses. And she is apparently ambiguous, but more likely male than female. So where is all of this coming from and what could be causing this? Not only that though, why would we want to do anything like this? So today's session is we're going to take a deep dive into this idea of facial recognition and look at one specific way of how faces can be recognized. We all do it intrinsically as people, but for computers, that's what's happening when it comes with the cameras, etc. It's a bit more difficult. And one specific way of doing it is geometric feature based. And that basically finds landmarks on your face, like your eyes, your nose, your mouth, edges of your faces. It positions them, finds the difference between each of them, and then it uses those as a way to classify you. So you could end up getting a load of landmarks or positions and distances and say these are for a male and do the same for a female. And if life was simple and straightforward, we could say something is either A or B, but as we know, it's not. So what's actually going on here? What are the building blocks for this technology? And where are the lapses? Where is bias coming in? And where are the algorithms not really up for purpose? So we're going to go through this and we're going to do it in stages. We're going to look at what the actual building blocks are for building this gender classification application, get you all set up. We're going to look at the data sets assets and the processing that needs to take place, how you train the model, and how you evaluate it. That might sound like a lot to do in 2 hours, but the purpose of this is it's a deep dive. So I'm going to talk through a few examples, then get you to try your own in each of these steps. And there's also going to be a load of notes. And there's going to be some things you'll understand and some things you won't. But at the end of this session, you'll get a complete working model for how to build such an application. And there'll be enough information for you to go on after this session and build it and develop it on your own. So the building blocks. First part is we need an image. If you are lucky enough so that your face is detected or in this image, then you want to kind of narrow in on that image and want to forget about all the other things that have nothing to do with your face. If you know anything about images, color images are what we call highly dimensional. There's lots and lots of information in there. Basic part is you've got blue, red, and green. And if we're looking for variation, maybe we want to simplify it. Rather than looking at the range of colors in blue, red, and green, what if we just looked at the variation from black and white? That simplifies things a bit more, and that's something we can do in the image processing. And then even further on from that, what if we got rid of some of the features that don't really matter? I mean, we all have cheeks and we all have foreheads and things like that, but what we call a landmark on our face would be our eyes, our nose, and our mouth. Those are things that we can identify as a face and clearly recognize. So we're going to use a system called Eigenfaces in order to take someone's grayscale photo and just reduce it to the landmarks. Then we'll feed it into a model and hopefully get back a classified gender, i.e. male or female. So we are going to do it using this method. So before I go into that, what I'd like you all to do is if you look in the chat, there's a set of instructions about how to actually get set up. So I'm going to give everyone 5 minutes to get set up. And if you have any questions, please put it in the chat or share your screen and we'll get everyone at the same stage. So I'll just walk through with you as well. So hopefully you have cloned the repo and I know where my repo is. So let's do this. So we've got Okay, so that's my repo, and I'm just going to do this to see what's inside it, and everything that I would expect to see is in there. So very first thing we want to do is we want to set up a virtual environment. So you've got instructions both for a Mac and also for a window. So as I've got a Mac, I'm going to do pip3 install. Okay. So I'm getting things like requirement already satisfied only because I've done it before. But that's basically meant that I can set up a virtual environment in my folder. Next, I'm actually going to create one. And I'm just going to call this face. So after the -m, you just put whatever you want the name of your virtual environment to be. Sorry, I'm also missing one instruction. So why is that not like that? Yep, wrong order, that's it. So that. Okay. And now I'm just going to type source face, and this is going to be how I activate it. And if you can see over here, I've now changed from being in my base directory to this virtual environment inside of my folder. So next, what I want to do is inside that, I want to install all of the dependencies I need. And the easiest way I can do that is if you look inside your in your folders, actually make that bigger, you'll all see that you have this thing over here, or you should have, and it's called requirements.txt. And let's just call it so. Good. And what that's basically doing is inside of that text script, it had all the dependencies you'd need for the project. So it's just going through it recursively and downloading everything you would need. Oh, sorry, let me know if anyone is running into any issues. Okay, we are good to go. I need to install my pip, but that's another issue. Okay, and then finally, I'm just going to install the main thing we're actually going to be working with, and that is something called OpenCV. Great. And now we are all good to go. So if we close my terminal and we launch our Jupyter notebooks, okay, that's all running in the background. Close that and let's get back to the slides. So what we're going to do is in the repo that I've sent through, you should find a list of photos in a folder. One folder will be named female and it would contain a load of female photos. The other would be male and it would contain a load of male photos. And the basic point we want to be able to do is get this model to understand male and female. Then further down the line, we want to give it an unknown and unseen face, and we want it to tell it whether it's male or female with a certain level of accuracy. So very first thing we said was we need to be able to detect a face in an image. And the way we're going to do that is by something known as Haar cascades. Like I said before, this is a quick overview, but the basic way this works, and it's one of the most popular and basic ways of detecting a object in an image, is by using what you call a cascade function. So we all know that with a face, for example, you're going to have a dark region where your eyes are, a lighter region where your forehead is, a lighter area where your cheeks are below your eyes. You'll have your nose. Your nose will generally be darker here, or there'll be a darker region here, and then lighter around here. And then you'll have your mouth, which will have a lighter area on top and to the sides. And so what these windows are doing is it's looking for those regions. So it's creating these windows of a certain size and it's moving along the image bit by bit. And it's trying to figure out, am I detecting those kind of light and dark regions? And is there a relationship between these light and dark regions? And this classifier has already been trained, so it can do it for faces, eyes, hands, and things like that. And so that's quite a good basis to start with. So all we're going to use now is use this very simple thing to see if there's a face in the image. Of course, depending on your face structure and to some extent your skin tone, those shadows are going to vary, but hopefully this should account for all of that. I say hopefully. So what you are going to be using is inside this classifier or inside Python, we are going to go about implementing this using a series of these functions. So first of all, we will import our classifier and we'll use the frontal face version. Some of you may have spotted we are taking our original image and we are going to turn that original image to gray or grayscale. And that is literally to reduce the complexity in the face. Then we're going to detect the face or detect the face in the image. So we take our grayscale image and then we've also got some other things in here. We've got things like the scale factor, minimum neighbors, min size and max size. All of those things do is they just give us an area to work with. So the min and max size say how large our windows are. The minimum neighbors say whenever you're taking this window and you're moving it across the image, it's saying how many of the windows next to it have to agree for the whole thing to agree we're detecting an eye or something like that. The scale factor, that comes into play when you're dealing with a photograph where you've got several faces, for example, because some faces may be closer to the camera than others. So the scale factor allows for that. So To see all of this put into place, what I'd like all of you now to do is to go to your Jupyter Notebook and go to the image cropping section. I'll just do that now and I'll bring mine up on the screen. Okay. Right, so here we've got the Jupyter Notebook. We've got data, so look in there. And in here is right, we shouldn't have anything yet. And then we've got some other things in there. We have inside of face, that's our virtual environment. And in model, we have our classifier already loaded. And then we've got a series of these, and we're going to go through each of these step by step. So we'll start with image cropping, then we will go to structure and data, then we'll go to data processing, eigenimages, and training our machine learning model before we actually make the pipeline that you saw in that app to make our gender classifier. So let's start here. So there's a series of things here, and to start with, we'll import them. And I've stored a group photo. And first thing I'll do is I'll say I want to read this one image. You can do that here, and we get the plot shown. I did that first using Matplot, which is what most people use for visualizing data, because that's what this photo is. It's a series of numbers from 0 to 255 representing a color, and it's all pixels. If I do this in terms of CV2, or see what that one does, that shows us exactly what I meant. So each of these values stand for one pixel, and that pixel translates to a color. And that color is a variety of blue, green, and red, and that can be quite complex. So what I can do instead is I can translate it to grayscale, which is what this is doing here. So that reduces the complexity. Then now I've got my classifier. So import that. And then next thing I'm going to do is I'm actually going to use this function. And this is the same thing you'll use and the same values as well. And so we've got the image and we've got these two values. So we're just literally using 1.5 and 5. And what that will help us do is that will work with the scale to make sure that we can detect the right number of images. If you've got any questions about that, there's a cheat sheet at the end of the document I send that will help you with that. So once it's actually detected the picture, we want to crop in on that, but we also want to be able to draw a rectangle around it. So first thing we do is we draw the rectangle. And what this does is it says X, Y, X plus W, Y plus H. And we've got this, and then we've got this. This tells us what the dimensions are. So the XY starts in the top left-hand corner. Then you measure to get to the next coordinate, that's X plus the width. To get down here, that will be Y plus the height. And then that will give you the coordinate over here. And so you can end up what your rectangle is. This is the color. So we've done 255. So that's going to give us a green outline. And the 2 just says how many pixels thick it is. So let's see what happens when we do that. Right, so most of the faces are recognized. We remember there was a couple of them in here as well that misclassified, but we'll come to that later. So we are just going to crop around first face we can pick, and it's just this one. It's the last one on the list. And we can also use this function to store it. What I'd like you all to do now is, I did that for one image. I'd like you all to try and do that for all the images in the female path and in the male path. So you've got some instructions here. So first, you've got this thing called glob. Glob is a module in Python, and what that does is it allows you to iterate through a list, and you can use some curly braces to kind of basically like regex or regular expressions, so you can iterate through it. So if we go back to here, in our data, we've got a file called female, and this might take a while because there's a lot of files in there. So let's go back. So if you look at female, all the files in here have the same structure, female underscore a number.jpg, and you'll find that the male one will be the same. So I want you to use a way of finding glob to basically bring back all of those path names, and I want you to save all of them under a new folder called crop female and another one called crop male. Then what I would like you to do is call a method on each of them to be able to put them in this actual folder. Does anyone have any questions? Any questions? Okay, great. I'm going to give you 10 minutes to do that, and we'll see what you come up with. But put something in the chat if you've got any questions at all. Okay, so just in case anyone needed any hints, I'll just put the first two bits. So we've got female underscore path will be glob, and it's just a path to the data. And we've got an asterisk here. And the reason we've got the asterisk there is it's basically a wildcard. And so it's going to take everything in there. And we know everything in there ends in JPEG. And it's saying with the mail, it goes to the folder called mail, and it literally takes every file in there that ends in JPEG. And we can print what that looks like. Just have a look. So we now have an array with all of the path names inside for the males or the male photos, and also for the female ones. So what we can do next is we can try and create a function, and that function is going to take the path in there. It's going to iterate over those paths, and we're also going to put the gender in there. Okay, so next clue. So we want to, for each of these images, we're going to want to read in the path, and we're going to use CV2 to do that. So the very first thing to do would be to do that. And then the next thing we want to be able to do is, remember, we need to change it from a color image to a grayscale image. Let me just check the indentation on that. Yeah, I thought so. Next. So now, if we have these parameters, we will, for each one, we'll say, look at the path, and I want to read the path in and store it under this variable called image, or IMG. I then want to take that image or that photo, and I want to change it from a color image to a grayscale image. Next, I want to be able to detect a face in it, and that is basically when we start using our hair cascades classifier. So first things first is we know that classifier is going to return the coordinates of where it's found the face. And so once we get that back, we then want to be able to iterate through that, or basically say, go through that image. And when we have this image, we either are going to store it under male, or we're going to store it under female. And that's going to come from the gender parameter we enter. So we're going to say for those dimensions, we're going to take it and then we're going to crop it. And we're going to call that our record of our image. Like so. Our indentations are awful. And then the next part we want to be able to do is we want to be able to call this for both male and female. So we know that when we put it in, we can say under gender, we can add male or we could add female. So we could say if the gender entered is male, then we're going to put it in one folder. And if it is female, you'll put it under another one. And so that is what we're going to do. So indentations again, I apologize. Cool. So we go through this. We're going to say, we're going to enter, we're going to have the path of a file, the gender of a file, and we're going to know the number that we've gone through. And then we're going to say, find in the image where our face is. And we're going to use this classifier. And once we've got those dimensions, we're going to crop the image because all of the rest is useless. Then we're going to say, if the gender entered for it is male, we are going to put that image, that cropped image or record of our image, into this folder here. And that's basically going to read male crop. And it's going to be the image, the gender, and it's going to be the number as shown here. And if it's female, do the other. So we can run that. Oops, we have, sorry, indentations again. And then we can run that for the female one. And we can also run that for the male one. Okay, and there we go. So do that, do that. And if we now go back and look in the folder where we had those images, before that we had nothing in our cropped files. Now, if we go in there, we now have them. And if we look inside, it should be pretty much cropped. Right, so that's the first stage. We have managed to get rid of a load of rubbish from our images. Now we want to actually start processing that in a bit more detail. So let's go here. Right. We have our cropped grayscales, right? And as you remember before, we have them and they're just like numbers which represent whether it's black, white, or anything in between. And at the moment, if you remember what happened when I showed you what CV2 does to it, we would get a 2-dimensional matrix. So we'll get something that looks like this. So for example, if there were 100 pixels across and 100 pixels down, we'd get a 100 times 100 array, or sorry, matrix. But we've got these images and we want to be able to store them and then retrieve them later without having to go through loads of different processes over and over again. And we also want to flatten things because it just makes it easier to store. And so one way to do that is to use something called a pickle. Pickle is just basically a way of serializing and deserializing a Python object. And it makes it easier to store and retrieve information without having to rerun machine learning models again. And in order to use that, we need to take a matrix and put it inside a one-dimensional array. And if we're working with a lot of data like that, easiest thing to do in Python is to use data frames from pandas. We use data frames because that allows us to analyze and also sort data. So we can do things like, if we had an entire column of data, we could actually write a function and then apply that to all the different entries in that column. So that makes life a lot easier. And we can also do something like data frame.describe. That can help us actually analyze it all at once, and we can get things like mean, standard deviation, and so on if we're dealing with a load of numbers. But one thing we really need to do, and one thing that would be important before we go down that road, would be to resize our images. Because at the moment, even though we've cropped the images will be of different sizes. We could have some images that are maybe 82 by 82, and then we could have other ones that are maybe 235 by 235. And that's not great because we want to have some sort of uniform structured data when we're trying to analyze it. So if we go over to the Python file or Jupyter Notebook that now is to do with image structuring, I can talk you through how to do that. So let's do that. So let's do structuring data. Okay, so again, just run through a few of these things. And this is also the same function we used before to be able to get a list of all the paths in. So we do that. This time we're going to add all the paths together. So we've just got one array to deal with, and that will make life a lot easier. And then we're just going to look at one of these images. So just the first one in that array. And we see that the size of this one is 182 by 182. So 182 pixels across and 182 pixels down. I actually went off and I kind of got the sizes of a whole load of other images. And so if we run that, we can see that actually, if we took a look, this is quite an array or quite a range of them. And if we look here, we got things like the mean is 149, and we've got a maximum of 273. So how about if we do that, we can get a much better look at what's going on. So just out of, I don't know, intuition, I'm going to say, why don't we resize everything to 100 by 100? Because if I look here, I can see we've got one down at 50. We've got 100 here, we've got one below it, and we've got quite a few ones larger. Compressing the images means you lose some information, but it's not so bad sometimes. But stretching images is not so great because you end up adding blur and noise into it. So I'm going to say just remove all, or basically remove all of the images that are below 90. Let's do that now. And then I'm going to have a look at what we've got left. Okay. And I'm going to run some analysis on these. And this first one says, get the image and grayscale it, then enlarge it, and that's where the intercube comes in, and then flatten it. So the original image was our matrix. Then we resized it, so it went from this large number, 74529, down to 19600. So that's our flattened size, and this is the array. So what I would like you to do now is do exactly the same, but do it for all of the images involved. So I will give you, this one's going to take a bit longer. Maybe let's go for 15 minutes. No, let's go for 20 minutes. Follow the instructions, and you've also got that cheat sheet to help you walk through it all. Okay, so let's take a recap over what we've done so far. So previously we had a load of images, and in each of those images there was a face. But we wanted to just concentrate on the faces, i.e. we wanted to focus in or crop the image so it just contained the face. And we did that by using functions from CV2 or the OpenCV library. And so then we've ended up now with 2 folders in a new crop folder. And each of these contain the cropped images of the male and the female photos. But next, what we want to do is we want to even simplify things even more. We want to get the sizes of them as well, have them in grayscale, and also we want to make sure the data is just more structured, i.e. we want to make sure the sizes of each of those images are the same. That will become more important or more apparent later on. So we've got to look at basically what the variation is in terms of the sizes of the images, and then we need to decide what the size is. If we've got an image and we try and enlarge it, we get a large image, but then we've got to fill in spaces that weren't there, and that can lead to misleading information. If we want to take a larger image and we want to downsize it, then that does lose information, but it doesn't cloud things as much. And as long as we don't reduce the size too much, then we won't end up losing too much information. So the first thing to do is we know that we can get the size of an image by basically using image.size. And what you would have noticed as well is that gets returned and you get 2 values, but the values are the same because it's basically come back as a square. So rather than getting both numbers, we can just get the first of each. So first thing we're going to do is we will define a function, and we will call this function getSize. So we've got def get size, and that's going to take the path of the image, and then we're going to say our new image that is going to be equal to this thing called image dot open the path. So the input is, it basically just reads the image in or the information of it. And then we will return the size of the image. I need to stop saying image so much. And we're just going to take that first number. Right, so that's good. And we'll just run it so that it's stored. Yes, there we go. Cool. Okay, next we want to create our data frame. So our data frame, we know that's coming from pandas. So we've got, we know we imported that as PD earlier. And then we'll say we want a data frame. And we're going to say the data, or basically all the entries in the column, is going to equal to basically the path we've got. And then we're going to say the columns are going to equal path. So, oops, what have I done? Pandas has no. Okay, let's double check I imported that correctly. So, pandas up. Give me one moment. Spelling mistake. Right, there we go. And then we want to be able to get the size on all the images. And this is what I said was the great thing about pandas. So we've got our data frame, which is basically just a table. And then what we can actually do is we can just apply that to all of them. So first of all, let me just show you what our original table looks like. So we end up with that. Then we can say we want to add a new column to it, and the values in that new column are going to be generated by a get size function. And then we will just have a look at what that looks like. So see, we now have a new column compared to the previous one, and we now have the size of all the different images. So now we want to be able to analyze that. One way we can do it, as I showed you before, was by using the describe method, right? But if we wanted to get a visual version, what we could do is we could create a histogram. And we do that, we can get a visual representation of what it actually looks like. And we do that using Matplot. And spelling mistake. Sweet. So if we look here, right, we have a few images that are very, very large, quite a few actually. So that is quite a few of them, like over 700. We have quite a few around 100. We have a few down here in comparison. They're around the 50 mark. So as a measure, we'll probably resize everything to about 100 by 100. Because like I said before, if we were to blow this image up to twice the size, i.e. go from 50 up to anything beyond 100, there would be a lot of noise in that and a lot of blur, and it wouldn't result in a good process. So first thing we can do is say, looking at that histogram, I want to get rid of any data less than 60. So get rid of this one. Do that. And then again, and let's have a look at that now. Actually, we can just do it this way. Okay. So we've lost quite a lot. We've now down to 2,587 images, but given what we're doing, that's still a good number. Next thing we want to be able to do is we want to determine from our table which path is female and which path is male. So next thing we can do is say, get a new function, and that function is going to take a string. And that string is basically going to be the path. And then we can say, using regular expressions, we are going to do that, indentation, that. So what we're going to say is take our string, split it where we get the underscore, or the first underscore, split it again when you get the dash, and then take the value there. And that, if we look here, is going to end up giving us this part here. Because we're saying take the first underscore, get the split, and then take the first thing after that. And so that will return us either the male or the female from the string, which is basically going to tell us if the image is male or female as we have defined it. And then next thing we're going to do is, just like we did with the resize, we can apply that to the table or data frame. And we should get a new column. Okay. And then the last thing we want to be able to do is, how do we actually get all this to flatten it? So that happens in quite a few steps. And I'm actually going to add a new cell for that. And this is getting into the stages of building up a pipeline in order to do a few of these things. So again, as I've done this before, what I'm going to do is I'm going to take what I wrote before and then paste it in here and then talk through it. Okay. So step one, as always, and like before, we want to read in the image. So in order to resize the image, we need the path to the image to do that. Then we're going to convert it into grayscale again, because that's going to simplify the complexity. It's been decided that it's going to be a 100 by 100 array, and that's just based on what we did before. So we want to say that any image greater than or equal to 100, we're going to shrink it. And that's where this thing comes in. So we say open CV library, resize our image that we've grayscaled to the dimensions of 100 by 100, and we know we're shrinking it. And if the image is below 100, we do the same thing. We say OpenCV, I want to resize my image, and I've grayscaled it, and we're going to enlarge it up to 100 by 100. And this CV2 or OpenCV2 dot intercubic is telling it that it's going to be enlarging it. And then finally, we want to take that result and flatten it. So we get that long string of 1 times 10,000 elements rather than our 100 by 100. So let's run all of this and see what happens. So do that. And this was a little something I wanted to show you. So I told you that we'd be taking images and we'll be serializing them and deserializing them. And I basically said, we're going to take a photo of someone, we're going to compress it to a load of numbers, we're going to compress it into an array. If we do that, can we actually get the images back? Well, let me show you that we can. So here we've said we're going to go to our table and we're going to reshape one of those bits of information for them. And we know that we want to reshape it to a 100 by 100 as opposed to 1 times 10,000, which happened when we flattened it. We know that it's going to be gray and we can get the label from it. What do we end up with? Right, so that's just because I haven't defined that. So let's take that back. And I believe that's just df. Take this one, sorry. Okay, okay, don't worry about that. That does actually work. Never do things live. I will fix that in a second, but let's run this. And that should also be. Okay, great. So what we've done is we've taken the data, compressed it again, and now we've saved it in a NumPy array, or we've pickled it. And now that data has been saved, that means that we can take it sometime later, use it, save it, and not have to go through all of that process again. And that has been saved on the data frame images. So let's have a look in our workspace. We go here, here, and there is our file. So that is all our images that's been compressed and can be used later for any of the machine learning that we want to be able to do. Right, so that was a bit of information and a bit of an overload. So next part is in terms of how to detect a face. So it is a lot of information, like I keep saying, but the purpose of this is to get a deep dive into the different components you need and then let you go away later and also think, okay, we're doing a lot of this stuff, compressing data, losing information, putting more information in. How does that affect how well something can identify something or classify something? I mean, we've seen as a very, very first step, we are turning things to grayscale. That won't necessarily be suitable for some faces or skin tones, but makes it easiest for us to run our algorithms. I mean, there are a series of trade-offs you'll see throughout this whole process that may make you think, is that trade-off really necessary or is there a better way? And that's why we need more people in these areas helping, because things like facial recognition are being used in loads and loads of different areas. It's being used for authentication, like our passports. Some of us can't use our passports at the e-gates. It's also being used, though, to help look for people. Imagine if you could have facial recognition to find a missing person. So there's good parts of it and there's bad parts of it. We just have to make sure that a variety of people are looking at all the different components and all the different building parts to make sure it's actually suitable and fit for use. And there's also the idea that just because you can do it, do you need to? Because I still, for the life of me, cannot understand why you want to use facial recognition to classify someone's gender. I mean, that's the same as trying to classify someone's race. That's something that should be owned by the individual, not by the outcome of a computer system. So moving on, let's go to the next part. So again, this is another step in terms of reducing information in order to make everything look, or basically make everything run faster. So next, when we actually do facial recognition, we don't actually use facial images. We use mathematical representations of the face. And one of these is eigenfaces. So how does eigenfaces work? Well, if you look at this picture, some of you may recognize her as Kelly Rowland from Destiny's Child, right? Let's say we drew a line, I don't know, across her lips or across her eyes. There'd be variation in terms of the shades from white to black, but in some directions, there'll be more variation than others. So let's say, for example, this represented a region around her eyes, right? So let's say here, for example, or like here. You'll get very little variation here. So there's not as much information, but there's a lot of variation along this line. So that's a lot more information. And when I say variation, I'm saying it from the mean. And the best way I can say that visually is just imagine it's the center here. How far do each of these vary from this center point here along this line? But then how far do they vary along this way here? So let's say we decided this was a good line to draw, where if we collapsed those points flat along that line, that we would keep the variation and not lose much data or much information. We could do that for hundreds of thousands of lines along her face, and we would find components or these lines. But again, we could rank these, can't we? Because some of these compressed lines of variation will be more variant than others. Or think of it another way. Some of these component lines will have more information in them than others. And those are the ones we want to keep. And what I've effectively described to you is something called principal component analysis. What that does is it takes those lines we've drawn and it ranks them. And what it will do is it will say the ones with the highest variance or the ones with the most information are going to be ranked first, and then so on and so on and so on. And so what you can do then is you can say, if I use all of the components, I might as well have just used the image. How many components, how many of these lines can I use and keep as much information as possible and not lose too much? And that's something you could do using these things here called principal components analysis. And that's another thing from a module in Python. So let me show you what that means in real life when you implement that in Python. So don't need that one, don't need that one, don't need that one, don't need that one. So go back to here and let's have a look at the eigenimages. Before we do that though, what we're going to do quickly is just going to run some data processing. This is not important, but what we're going to actually do before we run eigenimages is that what we're going to say is we've got male and female. And the male and female, it's not the best way to encode information. So we're going to use 0 and 1. So what that does is it say, basically what we're going to end up doing is say, if it has a gender of 1, then it's a female. If it has a gender of 0, we're going to say that it's a male, and that's what this does. And what we also did is we compressed the data. And what we said is rather than having numbers from 0 up to 300, what we're going to do is we're going to normalize everything and basically normalize all the numbers in all of our images so that it varies from 0 to 1. So that's encoding and normalizing. And again, that helps our program run. So that was a skip over, but again, if you go to the cheat sheet, there'll be some more information there. Next, eigenimages. So let's do this. We're going to load our data that we pickled from before. And let's see. One moment, I think. So let's just go double check that's there. Okay. And yep, so now we go back. Yeah. So sometimes you've got to wait for the things to run. I shouldn't be so impatient. Then what we're going to do is we're going to say we've got our independent features and what we call our target features. So we're going to say that the independent features, that's going to be what we've entered in terms of the images. And then our target ones, they're going to be 0 and 1. That is basically whether it's male or female. And this one is whether the independent features is whether it is, it's basically the images from the data that has been compressed. And we can actually have a look at those here. Apologies, everything. Sorry, I've run this. Again, impatient. So we've got 2,354 images, and then we've got 2,354 zeros and ones. Next, let's try and get these images done. So go here. So first of all, what we're going to do is we're going to run it and we're going to say, put our number of components as equal to 0 or none. And that basically means it's going to work on all of the components. So it's going to include every single component in the eigenimage. And then we're going to run a transform, see what happens. And we end up getting some information. And what we're going to do here is we're going to say, change this. Let's do that. And just run that. And give me one moment. Okay, that is not what I expected. So let's go back for a second. Okay, so that is not loading at the moment, but what we can do is I can say that from before, I know I've done this before, is I know that the ideal number to choose is going to be 50 components. So we can say, I want 50 components instead, and run it through there. So give me one moment. If you go to your eigenimages file, read through the instructions, and I will come back and talk you through the solutions. Okay, great. So we're back, right? So don't worry about before. So here we have the file. Just some mislabeled paths. Apologies for that. But here is our eigenimages file. So let me run this now and I can show you exactly what I meant from before. So run that. We've got our file of compressed data. And then here we go again. We can also look at what X looks like. Let's run that, right? And this is basically all of our normalized image data. And then we can have a look at what Y looks like. And Y is basically saying for each of those one-dimensional arrays of data, have we told it it's a 1 or a 0? So basically, each of those arrays, is it female or is it male? Great. And we can also have a look at the shape of that, which basically tells us the same thing. So we've got 2,355 files, and we've got 1 times 10,000 elements in the array, and then 2,355 ones and zeros, male and female. So next we're going to do the whole eigen faces or eigen images part. Again, don't worry too much about the detail of this because a lot of it is, there's a lot involved and there's a lot of maths involved in it. But the basic thing to understand from this part is, again, we're taking someone's face and we are compressing that information to make the machine learning process easier. We are losing information, but we are just taking into consideration the landmarks, the more important parts. But then again, importing information for one person's face might not be important information for another person's face. When we're running these algorithms, can we confidently say that we are accounting for a diverse group of faces and people? If we can't, then we might need to tweak how we use this. So do this. It's just a bit of the algorithm stuff. We can then have a look at what's actually happening when we reduce these images. So as I said before, what we're doing is we're looking at something known as principal component analysis. Don't worry so much about the image on the left, concentrate on the image on the right. Remember, I said that the PCA method is basically looking for lines, or it's drawing components which can compress information without losing too much information. And that's done by variance. But what it also does is it ranks them. So it says the component with the highest information, it ranks highly, and then goes down and down and down. And what we can do is we can get a cumulative ratio of these. And so what this graph here on the right is showing to us is what's known as the explained variance ratio. It's saying how many components can we have without losing too much information. Generally, 80% is a good value for this, because what happens if you have above 80%, you can lead to overfitting, but below 75%, it's not great. Looking at this graph now, it's a bit difficult to actually see the number because of the scale on the bottom. So what we can do is can quite easily see that not much happens above 300. So up here, I'm just going to type 300, and down here type 300 and see if we can get a better view. So yeah, so if we look now, we can see, like I said before, about 50 components gets us to just over or around roughly 80. And so that would be a good number of components or a good number of measurements of variance for us to compact our images. So now, instead of running this and saying n components is equal to none, we can say it's equal to 50. And what the other things do is, again, it just makes things easier. I know I say that a lot, but don't worry about that. So run that, run that. And what we now have is, rather than have 2,355 with a 10,000 element array, we've reduced it to 50 components. That's definitely going to make our algorithms faster, but at what expense? Again, we're going to serialize it, and we're going to use Pickle to do that. So import Pickle, write it to a file, and then we can consider some other things. So what we could actually do is we could try and have a look at some of these different functions as well. So we've serialized it. Let's see what happens if we bring it back. So this is the eigen image of somebody's face. So we took our original data, we ran the principal component analysis, we saved that data, and then what we've done again is we've brought it back. So we've reshaped it, and this is what we've got out. And again, just to say, the reason we do it that way is because pickling the data means we can save it and then we can bring it back without having to, basically without having to rerun things over and over again. So this is our last bit here. We're going to run that, save all of the data that we've put together. And then we've got the next stage. And the next stage is training the model. So we want to train our model. So I'm not going to talk you through these actually. What I'm just going to tell you is that when we want to train our model, we've basically said these are all our components. And we've actually also said these components belong to male and these other components belong to female. I want you to go through it. I want you to draw a hard line through these data sets to say, if a component looks like this, we're definitely going to put it under male. And when the components look like that, we're definitely going to put it under female. And then if I give you a new image, a new thing to compare, you're going to see how its components, its measures of variance are in comparison to the ones in male. And then we're going to see how that are in comparison to female. I expect you to then tell me whether you think the image I've told you is male or the image I've told you is female. And it's not going to be perfect, but we can also evaluate the model. And the way we do that is we divide all of the data we've got into two parts. First, we're going to train it on a series of data that we're giving it. I need to stop saying data, faces. And then afterwards, we're going to take that model and say, run that model over these known faces and see if you can actually figure out if we've said it's male or female. If you can, and you can do that to a high percentage, 90 or above, I'm okay with that as a model. If you can't, then things need to not change, but things need to be done. So the model has already been done. So what I would like you to do is run the file in your program that has the model in it. Just run it. Don't worry so much about anything else. But there's enough information in there so that if you want to tweak anything, you can tweak it later. And then lastly, what I would really like you to do is see if you can build this. See if you can build the pipeline, which I'm going to show you. So a lot has gone on today in this session. We have created a load of files and a load of tables with information. We've got one where we grayscaled the images, another where we stored these images as no longer an image, but an array of numbers. And then we have put a model on it. What I would like you to do is see, using all those files and all of that information from the previous files, can you follow these steps to actually build a pipeline? So define a function where it takes in the parameters image and image color. For each image, convert it to grayscale, then crop the face, normalize it, resize it, flatten it, subtract things from the mean, that's to do with the eigenfaces, and get an eigenimage, pass it to a machine learning model, get a gender out, and print the score. And everything you need to do is within these files to use, and everything or all the information you need is in these files here, and they've all been annotated. So I'm going to let you start it because we only have 15 minutes left. Give you 5 minutes to get started and see which ones go where. And then I'm going to talk you through it. And then we're going to build our model and then show you how it all fits together, and then test it out. Okay, so this is the final pipeline for the machine learning model. So these are all the files you'd need from before to be able to get the pipeline running. So run that, and great, everything has been loaded. What I've also said is that I'm going to have this thing here, and that's just our gender prefix. And that's going to be added to all the images we print. And then we've got this here, and all that's doing is just saying what the font is. So to start off with, we are going to put the images in, and we know already that the image is going to be in color, so that's RGB. Next, we want to convert those images to grayscale, which is what this line does. And this is going to run for every single image. Then we'll say, otherwise, if the image is basically not RGB, we've got BGR, which is just different ways of saying the same thing or formats. So we'll do it this way. Next, we want to crop the face. And we're going to do that using the HAR cascade classifier. And that's the thing we learned about in the very, very first file. So we've got our properties or parameters here. So the image, which is what we got from here, and making sure that the scaling and the nearest neighbors we have for each window are good enough to be able to pick up enough faces in the image. We know that faces, it brings us back coordinates. So it starts up in the top, I'm really bad at this, left-hand corner. It gives an XY coordinate, but then it also gives the width and it gives the height. So then we can get the opposite coordinate and we can make our rectangle. The other thing we have is we've got this part here, and it tells us what color we should draw the triangle in, and also how thick the triangle should be. So we're going to say the record of our image is equal to this, which is basically a cropped version. So we're saying take the image, but only return the image that fits within these parameters, this height and this width, or these XY coordinates. We are going to normalize the data. So rather than going from 0 to 255, we go from 0 to 1, which is what this part is. And the reason for that is you could have some images that only vary from white to light gray, but you could have other images that vary from dark gray to black. And so what we want to do is normalize all of that. Again, that's another stage. Your information will be lost, but it helps with the algorithm processing. Next, again, we're going to do this process of reshaping the images. And the reason we do that is, again, because we want to unify everything. So we're going to say, we've set our boundary at 100. If the image is below 100, we're going to enlarge it. If the image is above 100, just like XY width height, then we're going to shrink it. Again, like I said before, shrinking images, you do lose information, but enlarging images, you're putting information that's not there. So the tendency is to shrink things rather than enlarge them. But yeah. Then we will resize it. And rather than storing it as like 100 by 100 numbers, we're going to store it as a one-dimensional array, which is going to have 10,000 elements in it. Then this is what I call the black box area. So we turn the images into eigen images, which basically looks like those scary images I saw before that make you look like a face, but those show the landmarks of a face, so important information, and loses more information. And then the last thing is we're going to run it against our model. And we're also going to try and get our model to predict the images. And that's what you saw in the app before. So we can run this. And then we will run this, and yep, we end up with a female actress being identified as male to some extent. But we could also have a look at something else, which is, let's have a look at this. We can also get males identified as female. So obviously there's some tweaking to be done in general. So thank you for listening. I hope you found that helpful. In the sheets I shared, um, there's the to-do version that you can follow along with, and there's also a complete version as well. So this was a deep dive into the building blocks of building a face classification application. And as you obviously saw along the way, every single step was about reducing noise or unimportant information and focusing in on what we call the important information. And that was for the purposes of storing and retrieving the data, and also for the purposes of making sure the algorithms run fast and not slow. So taking faces, which are naturally highly complex objects, and simplifying them so that a computer can see them and then classify them. I still don't know why you would want to use someone's face to classify their gender, but I can understand why you would use someone's face to identify them as them. But given that this is technology that's to be used for everyone, not just the norm, if you fall outside of that norm or outside of the norm of what people think this technology should be used for, clearly you're going to be misclassified, misgendered, misidentified, and so on and so on. And there are several steps that happened along. You had the image part. So what's going on in terms of making sure the images used are up to standard and correct. We have the reduction and data processing side. I mean, is storing of information in today's age really more important, or basically the ease at which you can store information more important than losing information? And then what about these boundaries and these classes? When you go around saying, I want one thing classed as one and one thing classed as another, again, that is down to someone's opinion. And that's another area where we need more people and more diverse people working so that everything is not just done in terms of one group's opinion, but technology is made so that everyone can be included. Thank you for listening.